Howdy folks, welcome back to CS 128 Honors. In today's lecture, we're going to be covering some more stuff on threads in Rust and how threads interact with ownership and the Rust's memory management model. So today we're going to be answering some of your questions at the beginning, then going through some thread joining and tracing through some multi-threaded code so you guys can get a little bit better at sort of reasoning through what's going on. Then we're going to review MPSC and the drop trait and show you some more sort of cool things that you could do with that. And then at the end, talk more on thread execution order and how that sort of interacts with ownership. Okay, just a couple of quick reminders. So homework 9 is going to be due this Thursday at midnight. We did not release homework 10 last Thursday, so we're going to be releasing it today. It's going to be due in a week at midnight. MP3 will be releasing today. It'll be due in 2 Fridays at midnight. And just a quick reminder, we're going to be having our first in-person social/office hours tomorrow from noon to 2. I will follow up with the room in the Discord channel. Okay, so let's get into some of your questions from Prairie Learn. So we're throwing around all these words: clone, reference, pointer. These can be very confusing, especially since they're very different in Rust than what you see normally in other languages. So let's touch briefly on these, and then we'll keep talking about them throughout the lecture. So clone is some deep copy of some data. If I have some piece of data here, some vector, maybe a hash map, whatever it is, and I want to make a clone, I take a deep copy of it. So I look at all of the elements inside of it, I look at all of the fields, and I copy them to a separate copy. So if I modify the original copy, nothing will happen to the new copy. And if I modify the new copy, nothing will happen to the original. So you're creating 2 independent copies so that you can sort of manipulate them independent of each other. So we'll see why this is useful in threads later down in the lecture. Okay, so deep copy is just a piece of data with identical fields, but they do not share any references to the same data. So they're independent. You can modify them as you like without having one affect the other. Okay, and so we call .clone in Rust when we want to sort of make a deep copy of some data that's expensive, because making deep copies can be time-consuming, resource-intensive, whatever it may be. We don't have to copy things like integers, booleans, primitive types, because those are simple to copy. They're just a number. You can, copy them over, move it from one register to another. Things like strings, vectors, hash maps, you have to go through every single one of those elements. There could be potentially millions of things to copy. So calling .clone is this explicit call, and you're telling Rust, hey, I know this can be time-consuming, but I want to do it anyways. So you get what you ask for. Okay, so we've been throwing around this word pointer as well. So a pointer is simply just some address in memory. So memory is addressed at 0 and goes all the way to whatever the highest address is. A pointer is some address, some location in memory where there's data we're interested in. So if you have, say, something on the heap, you have a pointer to that data on the heap, and you can sort of access it that way. You could have a pointer to something on the stack. A pointer is simply a memory address, and you're interested in the data at that address. So the issue with pointers is that this data might be invalid, deleted, corrupted, or whatever if it's no longer in use. You have no guarantees that it's valid if the data has been deallocated, it's been its lifetime is ended. So Rust makes this assumption that data could be invalid at any point. So you're never going to interact with pointers just by themselves. Rust guarantees memory safety, so you'll never interact with raw pointers in safe Rust code. So there's this thing called unsafe Rust code, which allows you to do things like manipulate pointers, but you're never really going to be sort of touching this. If you look at the Rust-Lang source code, you can sort of see interacting with pointers in Rust, but we're never going to be doing this. So there is this notion of smart pointers, which is some piece of data, and you have a pointer to that, but you're only going to be interacting with the smart pointer. So smart pointer allows you to simply just manipulate that data directly, since it handles all of the pointer manipulation for you. Okay. And then we have this word reference. So in other languages, this might be different, but a reference in Rust is simply a pointer that is guaranteed to be valid. So Rust guarantees validity by this thing called lifetimes. This is a topic for a future lecture because it is an entirely new concept in its own, but safe to say a reference is simply a pointer to some data that you know is going to be valid, and Rust will not allow you to take a reference if that data is invalid. So whenever you're making a reference, whenever you're making a borrow, you are actually getting a pointer that is guaranteed to be valid in the form of a reference. Okay. So we had a couple questions to go over the linked list homework. So you've seen this as ref method. This can be slightly confusing because it might get confused with taking actual borrows in Rust in the ampersand. This is an option specific method. So asref converts a borrow to some option to an option that borrows the data. So remember from ownership, whenever we have some data inside a type, that type, so this option, owns this data. And so if we have a borrow to this option, what we can do is we can create a new option, but the option contains a borrow to the data. So slightly confusing, but this is super useful when we want to sort of manipulate the inside link or check the inside link, see if there's some data that we want, see if there's some valid links, whatever it may be. It's hard to manipulate the option itself, so asref gives us a reference to the data inside. Like I said, this is an option-specific method. Other types can choose to implement this method if they like, but asref is primarily seen in option types. And you also probably saw asmute. Asmute acts the same way, except it takes a mutable borrow to an option and gives you an option with a mutable borrow to the data inside it. So the data T here is the same that's in this data here. It's the same actual piece of data. We're just taking a borrow to it. And so same principle as asref, it's just with mutable references, and the same ownership and borrowing rules that you've been learning about apply here. So you can only call asmute on one option at a time as in one scope. So once that scope goes out of scope, then you can call another asmute. But you can only have one mutable reference, so only one call to asmute in some scope. And asref, you can have as many as you want as long as there's no sort of mutable borrows. So same ownership rules, just a simple convenience method to help you interact with options. Okay. So for homework 9, if we were to join each thread in a vector, so we have a vector of join handles and we want to call join on each handle, why does it run every thread in parallel? So good question. So I thought the join call would call on each thread and force the main method to wait until the thread is finished, which then may move on to the next thread. So join is there to wait for the thread to finish, but it doesn't tell when the thread should run. So thread spawn tells the thread when to run, and join just says in the main thread or whatever thread that you're in, wait for this specific thread to finish. So you have no sort of guarantees on when it can run. It can run anytime once you call thread spawn. Join just simply means wait. So we'll walk through an example in the next couple slides. So join blocks the current thread, and so presumably by the time you call join, you've created all of the threads you want. And so this means our threads are already running, and so once we call join, we're simply waiting for all of our threads to finish. So the order threads are waited on is not connected to how they run, as long as the threads are all created before any join happens. So let's walk through this code. I wrote this as a little bit of an experiment. So we're creating 5 threads. We have this little for loop, and then we say thread spawn, get our handle from that, and save that handle. And so inside of our threads, we're going to first print hello, then sleep for 1 second, then call hello again, sleep for 1,000 seconds, say hello again. So throughout this thread, we'll be sort of saying hello 4 times and sleeping 3 times in between. And then in our main function, we are also calling join on these join handles, but we have this little start and duration variables. So start basically says take a timestamp when this code runs. And so we take a timestamp, then we wait for the thread to join, and then once that thread joins, we call get me a timestamp again after the thread joins, and we take like the duration, so the difference in times between before the join and after the join. And then we're going to print that out, how long we've been waiting. Okay. So I want to quickly reason through this, walk through what's going on. So we spawn all of our threads, and then we wait for them to join. Okay. So we start out with our main thread. Our code starts. We create our program, called cargo run, whatever it may be. And then we create our 5 threads. So we got thread 0, 1, 2, 3, and 4. And so you notice there's a little bit of an offset because we're creating thread 0 first, and then there may be a little bit of overhead to create it, then thread 1, a little bit of overhead, so on and so forth. Okay. So once we've created the 4 threads, our main thread continues on to the outer loop. So the main thread, we create our threads, and then it continues past this for loop to the second for loop. And then it takes a timestamp and then blocks. So our main thread continues on. Once we create thread 4, we begin waiting on thread 0 to join in our main thread. Okay, so the main thread is currently waiting on thread 0. And then our threads continue to run. So this is the first time printing. There's a little bit of a sleep here. Maybe thread 0, 1, 3, and 4 sleep for a little bit longer than 1 second. You have no guarantee on when they actually run. Then we sleep again. These threads run, they print out hello. Finally, we see thread 2, it prints out hello, and then finishes. Then thread 0, it prints out hello, and then finishes. And so the main thread has been waiting on thread 0 to join ever since we created the 4 threads, or the 5 threads. So at this point, thread 0 joins, since thread 0 is finished. So now we begin waiting on thread 1. So thread 1 runs, finishes, and so once thread 0 joins, we're waiting on thread 1. We see that thread 1 is finished, so then thread 1 joins. And because thread 2 has already finished, we don't need to wait on it. It finished before thread 0, but because we waited on thread 2 after thread 0, there's no sort of wait time between thread 1 and thread 3. Okay, so thread 1 and 2 joined. We're waiting on thread 3. Thread 3 runs, finishes, prints hello for the last time. We see that thread 3 joined, so we're going to begin waiting on thread 4. Thread 4 runs. Let me hide my camera here. Thread 4 runs, and we're waiting on it. We see that thread 4 has joined, and that is the end of the main thread. So the big takeaway is we spawn the 4 threads, and the main thread is now waiting on thread 0. And it waits for this long period of time, at least 3 seconds, because we're sleeping 3 times for each thread. And then finally, once thread 0 joins, there's these short little waiting periods for the remaining threads because there's just sort of a little bit of overlap, but not much. Okay, so let's go ahead and run this in VS Code. Let's see what happens. So we have our handles, create 5 threads. In each thread, we're going to print hello 4 times, sleep in between them, and then take the timestamps. So we see we're saying hello, and then we join. So our main thread is waiting for thread 0, and so we're waiting for thread 0 for almost 3 seconds, just a little bit over. And then once thread 0 finishes, we're waiting for threads 1, 2, 3, and 4 for a very short amount of time. So what I want you to take away from this is when we create our threads, they run independently of the main thread. We're not waiting for threads to spawn another thread. We spawn all of our threads at once, spawn thread 0, then 1, then 2. And so once we call thread spawn, our threads are already running. Join just says stop the main thread. So the main thread stops here, but we've already created our threads before the join. So that's why when we call join, we're not waiting for threads to finish before spawning another thread. Okay. So like our hypothesis said, we sort of wait for a long time on thread 0, and then the wait times for 1, 2, 3, and 4 are fairly minimal. Okay, let's briefly review MPSC, multiple producer, single consumer, from last lecture. So like I said, MPSC, multiple producer, single consumer. You have this notion of senders, these clonable transmitters that you sort of give to many threads, and they all send to one receiver. So you create your channel, then you can clone the sender that you get from that channel, give a cloned sender to each thread, and every thread will send messages to the one receiver that you make. So clone the transmitter, move that cloned transmitter to a thread, and then you can send messages within your thread, and then finally receive messages on your main thread with your receiver. Okay. And then we talked about how to solve problems with parallelism and MPSC channels. So we have our main thread with some large piece of data, and we split it up into these chunks. We'll talk more about why we want to split these up today. So we said that we want to split the original data and convert it to an owned value. Okay, and then we give each owned value to a thread using the move keyword, perform some computation within each thread, get a result, finally send each result back to the main thread using our channels and our senders and receivers. And then we have some logic in the main thread to combine each of these results and give us our final result. Okay, so why do we actually need these owned values? Well, let's talk about that. Okay, before we do that, we had this drop call here from MPSC. So we want to drop our original transmitter because receiver will block until all messages have received and all transmitters have been dropped. So all of our clone transmitters drop when our threads finish, but we still have the original transmitter. And so this code will never finish because we have the original transmitter, so we got to drop it. So when you have when you're receiving and creating your threads in the same function, you have to have this drop. So like we said, receive returns an error when all transmitters have been dropped and all messages have been received. And so we're saying loop while we get an OK. We're never going to get an error while the receive is blocking. So receive finally returns an error and stops blocking when you've gotten all messages and all transmitters have been dropped. So we said transmitters are dropped when they go out of scope, or you call drop on them. And so we said Rust automatically calls drop when a variable goes out of scope, so when the thread finishes, but you can do it ahead of time. So we can sort of get around this. We can get around having to call drop ourselves. So we said transmitters are dropped when they go out of scope. So we can force the transmitter to go out of scope. So if we have this function split work and create threads, we're going to call this somewhere in our main. But in this function, we're creating our channel, creating our threads, moving the owned data, this 2vex, let's create an owned piece of some vector, create a clone of the transmitter, and do our logic with the thread. Well, at the end, if we return receiver, transmitter is going to get dropped at the end because transmitter goes out of scope. So the clones go out of scope in the threads, and the original transmitter goes out of scope in this function. So each cloned tx goes out of scope when the thread ends, and tx, the original transmitter from the channel, gets dropped from memory at the end of this function because Rust will call drop tx for you. Okay, and so then we return our receiver, and we pass this receiver into some other function called receive. We have our little loop here. While receive gives us an OK, print out that we got some value and add it to our total, and then continue blocking until all transmitters have been dropped. So receive will block until all messages are received. We know all transmitters are dropped because at this point, when the threads finish, they're dropped, and at the end of this function, our transmitter is dropped. Okay, and then in our main, we create our piece of data, call this split work and create threads function, and then pass the receiver that we get from that into this receive function that we just made up here. And so there's this blocking call in receive. So receive will block the main thread. That's the important bit. because rx.receive blocks this function, the main thread will also get blocked because you're calling receive in there. So that is a big hint for MP2. You're going to be creating two separate functions, one to split work and create threads, and one function to receive. So you're going to be using this model, so you do not need to call droptx because Rust will call it for you. Okay. Now let's talk about threads and ownership and why we want to have these separate pieces of data when we're creating our threads. So a thread owns all of the variables that are moved into it from the parent thread. And we said this because we have the move keyword, and we sort of move ownership of values that cannot be copied and clone values that can be copied, so primitive types. Or sorry, copy primitive types. Okay. And then we said variables, values, etc., they all get dropped when they go out of scope. So when a thread's finished, all of the variables that a thread owns go out of scope. So the data that the thread owns gets dropped when the thread finishes. This includes the main thread. And so the big takeaway is we want our threads to own their own data to guarantee memory safety. If some thread owns some piece of data, we do not want another thread to also be looking at that piece of data because that data might go out of scope. And so then we get an invalid reference. And we'll see what this means in the next few slides. So, like I said, why do we want this? So let's just suppose we do share data. Let's suppose that we have this shared data in the main thread. We take an immutable reference, give that to thread 1. So we take a slice of our data, this little bit here. Then we take another immutable reference, the middle slice of our data, give that to thread 2, and then a final slice, give that to thread 3. Okay, and then each thread will sort of act on that slice, give us a result, and then yield our final result. So in the last couple lectures, we've talked about thread execution order. So I want to see if you can spot the issue of giving immutable references given these sort of thread orderings. So the very first sort of order of execution we could get is we have the main thread, then thread 1 and thread 2 and thread 3, all at the same time. That's one possible execution order. Another one is we have the main thread running and then maybe thread 1 runs sort of halfway through, and then thread 2 runs halfway through after that. It's another possible ordering. Or we could have no overlap. The main thread runs, then thread 1 runs, thread 2 runs. The biggest thing I want to note here is there's no guarantee of joins. So Rust is not really smart enough to notice that you have a join here and you're waiting for something to finish. So you sort of, as a programmer, have to be proactive and guarantee that memory safety because Rust cannot do that with joins. Okay. You could also have this execution order. You could have a main thread running for a little bit, thread 1 and 2, maybe they'll sleep for a little bit, maybe some other process on your computer is going to run, then thread 2 continues running, more work on thread 1, more work on the main thread, thread 2 sleeps for a while, and finally you finish the main thread and finish thread 2. That's another possible execution order. You have no guarantee of how your computer runs these processes and threads for you. Another example. So there's no guarantee of this execution order. So why is that an issue for us? Well, let's just consider this basic one. The main thread, thread 1, and thread 2. Well, we said when a thread finishes, all of its data gets dropped. So if we have this shared data in the main thread, well, that data will get dropped when the main thread finishes. So halfway through the execution, thread 1 will have an invalid reference to the data because the data gets dropped, it no longer exists, it's corrupted. Again, in the second example, data gets dropped, the shared data gets dropped when the main thread finishes. So at this point, all of our references to the shared data become invalid because that shared data goes out of scope, it's dropped, you have no guarantees that it's there anymore. And so, like we said, references in Rust are pointers that must always be valid. So if we're sort of giving shared data to threads, we have to have a guarantee that it's going to be valid the entire time every thread is running. And so we cannot do that because there's no guarantee on when the threads will run. You have no guarantee on execution order. which means you cannot guarantee that data will be valid for the entire lifetime unless you use some more sort of advanced types and advanced tricks in Rust. And we'll be talking about those in a couple lectures down the road, but we cannot do that with just basic immutable references. Okay, so this is why we want each thread to have its own copy of the data. So even if the main thread goes out of scope, thread 1 owns this data. This data will only go out of scope when thread 1 finishes. This is independent of the original. It's not a slice, it's a deep copy. Okay. So going back to this thread execution order, the original data gets dropped at the end of the main thread, but thread 1 owns a deep copy. It owns its own piece of data. So thread 1 can continue on. It'll continue working because it has its own piece of data. We do not violate any, memory rules. Nothing bad happens. And then thread's 1 copy of the data goes out of scope when thread 1 finishes. Thread 2's copy goes out of scope when thread 2 finishes. Each copy of data is independent, so we're not sort of causing any memory issues. We're not creating any invalid pointers, any invalid references, whatever the case may be. So we obey Rust's borrowing rules, and nothing bad happens. Okay, so I've been talking a lot about sort of giving owned copies of data to threads, and so I'm going to show you what that looks like in the context of MP3. So you're going to want to split up your data into owned chunks. So if you have a vector in MP3, it's going to be a vector of strings. Then you're going to create a vector of strings. So if you have 1,000 elements in your original vector, you're going to create, say, 10 threads, and you're going to give each thread a copy of your data. So one thread gets one of your subvectors, each with 100 elements. So 1,000 elements get split into 10 vectors because 10 threads, 10 vectors of 100 elements. So each thread works on a portion of your original data, but you're creating an owned copy. This is not a reference. It's a deep copy. It's a clone. So you're giving each thread some owned copy to work with. Okay. MP3, you're going to take a vector of strings, clone each string, and place the clone into one of your subvectors inside the outer chunks vector. So we're going to reference the inner vector as chunk, because you're giving a chunk of the data to each thread, and the outer vector is your vector of chunks. Okay. And so you're going to use an iterator that takes ownership and consumes your data when you're going to be sending your individual chunks to your new threads. So going back all the way to the ownership and borrowing lecture with vectors, call our function to split our data into chunks. We borrow the original data. We're going to clone, the individual strings inside, get an owned copy, a vector of vectors, vector of chunks. Okay, and this is where we use our iterator. So into_iter is going to take ownership of chunks, and it's going to give you an owned copy, or the owned data inside of your vector. So chunk is owned, so you can move that owned copy into the thread. So this into_iter is super, super important. Chunks into_iter, and then move that chunk into your thread, call thread spawn, do whatever computation you'd like on chunk, and then continue on. So use into_iter to get owned elements of your chunks vector. So you move the owned chunk into your thread. Okay. Hopefully this helps you get started on MP3. We will be releasing a sort of hints video on MP3 as well. Apologies for not getting that out for MP2. MP3 is a super, super cool sort of MP that models MapReduce, this Google's sort of distributed computing system. So you're going to be creating a small sort of toy MapReduce in Rust. So more on that in the intro video. But for now, that's all, folks. Thank you for hanging in there. Take care.